So sec theta is 1 over cos theta, cosec theta is 1 over sin theta, cot theta is 1 over tan theta. We did that yesterday. Hopefully you're comfortable with those relationships. That is they're just fact. I can't prove that. They are names to the reciprocal ratio, so we're defining those. Also recall these two identities. We've not really formalised it, but it's come up a few times. So it came up in the last couple of weeks when we did the unit circle review, and certainly I believe it came up in both methods classes as well early this year when you're talking about it. So you've seen this. We're really going to start using them now. So we had the tangent identity and we had the Pythagorean identity. This is always called the Pythagorean identity. This that kind of name doesn't really stick, tangent identity. So it might be called other things as well. And here's a quick note on that. Just recall that they come from this. I just copy paste this from what we did last week. The unit circle is there. And if we have a unit circle as a radius of 1, we define theta as the angle between the positive x-axis and a point pxy on the circle. Typically it's easy to visualise this if the p is in the first quadrant. And we'll get, of course, x is equal to, or sorry, cos theta is equal to adjacent over hypotenuse, which is the x value over 1. So x equals cos theta, y equals sin theta. And this leads to the fact that first sine squared plus cos squared equals 1 squared. That's Pythagoras. And you get the Pythagorean identity. It also leads to the fact that tan is opposite over adjacent, which is sine over cos.
What does it mean for square in front of the theta again?
Here, yeah. So that is the difference between, it's a good question and it's important. So if I write sine theta squared like this, a calculator would treat it like this, sine theta squared. So that's, you're telling the calculator, you're just telling whoever's reading it to square the theta and then apply the sine, because that's what happens in our order of operations. Whereas if you want to square the whole thing, if you want this sine theta all squared, then we have to have a different notation. If we want to do the sine before we square, and so our different notation is we write it like that.
So we put it in a calculator like that.
If you want to put this, if you want to square sine theta, you have to put it in brackets in your calculator. Sorry? What doesn't... Oh, sine squared theta? Yeah. Yes, well that was something we were going to talk about at the end of yesterday. It's not quite in the curriculum, but it is an interesting function. But it just takes all the negatives and pops it up. Yeah. And then because it's squaring, it makes it a bit of a square graph, doesn't it? Yeah. Yeah, so it does. It looks like the bottom set of teeth. We've got teeth again. How good is that? Yeah. I think it is. Okay. So this leads naturally to a couple of things. And I've got a y question mark there. I'm going to show you why. First of all, cot theta equals cos theta over sin theta. We did talk briefly about this yesterday. The y on this is because we know that tan theta is equal to sin theta over cos theta. And therefore, cot theta, which by definition is equal to 1 over tan theta, is equal to 1 over sin theta cos theta. And if we divide by a fraction, we multiply by the reciprocal, and so it gives us cos theta over sin theta. So hopefully that's fairly obvious, which means you don't have to memorise that. Like tan theta is sin over cos, cot theta cos over sin. That should be fairly trivial. This one here, cos squared theta plus sin squared theta equals 1. Divide through by cos squared theta, and I get cos squared theta over cos squared theta plus sin squared theta over cos squared theta equals 1 over cos squared theta. And they cancel out, obviously, to give me 1. Sin squared theta over cos squared theta is tan squared theta. And 1 over cos squared theta is sec squared theta. And so we have identity 1. We got identity 2 by doing the same process but dividing through by sin squared theta instead of cos squared theta. And it works, okay? So that's where those identities come from. So now we have the Pythagorean identities. So, or you might say, you know, the Pythagorean identity relates tan and sec or whatever. But you'll see this. So we're going to do identity proofs. That's what this topic's mostly about. you performing proofs on identities, and I like it, so I might get a bit excited about it. You maybe not quite so much. But if you see a question and it's got tans and secs in there, then you're dealing with probably that second one. And you know you've got to look for using that second one. If you see one with cot and cosec, and they're both in the identity, you're probably going to make some sort of substitution at some point. Okay, and you might see cosec appear and tan. You know that tan is 1 over cot, so you can get to that cot-cosec relationship and use it. So you're just going to be using these, and you know that these have a nice paired relationship that you can use. So I'd be looking for that opportunity. We're going to do some examples, and I'm going to give you some time. So example 1, if cot theta equals 5 over 12, calculate the value of sine theta. Do we have a relationship between cot theta and sine theta?
Yes.
What's the relationship between cot theta and sine theta?
Well, cot squared theta equals 1 plus 1 equals cosec squared theta.
Okay, well, shall we follow that path?
Yes.
Okay, so let's square cot theta then. So we get cot squared theta, 25 over 144, the pinnacle of the times tables in primary school, 144. And now let's add 1 to that, shall we? So we get 1 plus cot squared theta is equal to 25 plus 144 is 169 over 144. And so this is now cosec of Mr. C. Squared theta is equal to 169 over 144. And what's cosec squared theta in terms of sine squared theta?
1 over sine theta.
Excellent. So if we reciprocate that, we get sine squared theta is equal to 144 over 169. And of course that means, and we are taking a square root here, so we've got to be a bit careful, that sine theta is equal to plus or minus 12 over 13. 144 is 12 squared, 169 is 13 squared. Okay? If you get this type of question, there's a few ways you can do it. But you do have to recognise that you could get negatives and positives. This is the best way to do it, to guarantee that those negatives and positives appear at the right time, because there is 2 possible solutions. Because cot theta is like tan theta. It's positive in quadrant 1 and 3, but sine is positive in quadrant 1 and 2. So it's negative in 3, positive in 1, so depending on whether the cot is in 1 or 3, sine could be negative or positive. The other way you could do it is you go, well, if cot theta equals 5 over 12, then this is equal to, remember tan is opposite over adjacent, so cot theta is adjacent over opposite. This is adjacent over opposite. So we have a right angle triangle where adjacent equals 5 and opposite equals 12. So I could draw that triangle. And there's my right angle. There's theta. What did I say? Adjacent equals 5. So my scale is pretty poor, but that's all right. Opposite's 12. I do Pythagoras, I get 13. Sine theta in this triangle is opposite over hypotenuse. So therefore, sine theta equals 12 over 13. So that's another way you could do it. And you know, there's a couple others. So you can play with whatever you want. The problem with this, though, is that it's not obvious that sine theta could also be negative, because we've only dealt with theta as a first quadrant angle. So you've got to recognise that cot theta could be positive in the first or the third quadrant. And so if this angle is actually a third quadrant angle, sine will be negative. So we have to make that recognition and put in a negative possibility as well. So I'll let you play with that, and you can deal with those questions however you want. Are there any questions on that? I would recommend, just for the benefit of the proofs you're going to be doing, that you just practice the first method. It gives you the obvious plus and minus, and it falls in line with the proof you're doing as well. Example 2, and that's it. So example 2 says, prove that 1 minus sec squared theta times cosec squared theta minus 1 equals 1. And part B, prove that cos theta equals cosec theta over tan theta plus cot theta. So B, I think, is a bit harder. A is not too bad. So I'm going to just write down quickly our relationships that we know over here. We know that cos squared theta plus sine squared theta equals 1. We know that 1 plus tan squared theta equals sec squared theta, and we know that cot squared theta plus 1 equals cosec squared theta. So, what do we get from that?
We get cosec minus 1 equals cot squared theta.
1, 2, 3. So from 3, cosec
Then, so the first bracket is tan squared theta.
minus 1 equals cot squared theta. And 1 minus sec, I'll get a feeling this should actually be negative 1. So in A, we get 1 minus sec squared theta, and cosec squared theta minus 1 is equal to 1 minus sec squared theta is, so from 2, is it 10?
Yeah.
I think it's negative 10, which means I may have copied this example down incorrectly. So for this relationship here, I have to subtract tan and then subtract sine sec squared theta. So I get this, I get negative tan squared theta times by cot squared theta, and that's equal to negative sine squared theta over cos squared theta times, I could have done this just as cot becomes 1 over tan squared, I suppose. That cancels, it's equal to negative 1. Let's just pretend that never happened. Negative 1. So that's me copying it down wrong probably, but you see the process we followed there. Now there are other ways you could have done this. This would have worked in heaps of different ways. So if you don't see this relationship here, you could have expanded those brackets and then gone, oh, okay, I've got a sec squared theta, I know that's equal to 1 plus 10. You could have built an understanding from that and it would have worked. But you're looking for the quicker ways as well. So today and in the next week or so, when you're doing these problems, do it your way and then talk to people on your table and see how they did it. And see if people did it in quicker, more intuitive ways and practice those skills because you need that time in your exam. Question B, and then I'll finish this bit. Prove that cos theta equals cosec theta over tan theta plus cot theta. Now, it was a bit more obvious in A, but for B, we've got two sides that we can manipulate, but the right-hand side is clearly a lot more complex, and therefore there's a lot more I can do with it. So I'm actually going to take the right-hand side and forget the left-hand side. I'm going to try and make the right-hand side into cos theta. And I'm also more comfortable with cos, sine and tan. So not only am I going to do that, I'm going to move everything to cos, sine and tan. So I get cosec theta over tan theta plus cot theta, which is equal to, I'm going to write this down as, well, I might leave that as cosec for a little while, and I'll explain why a little bit later. I just don't want double fractions. But I'm going to write this down as tan theta plus 1 over tan theta. And then I'm going to simplify that by writing it down as cosec theta over tan squared theta over tan theta plus 1 over tan theta. And so now I can write this down as cosec, and sometimes these will take a while to get out, tan squared theta plus 1 over tan theta. And when we divide by a fraction, what do? We can multiply by the reciprocal. So I'm now going to write 1 over cosec theta as 1 over sine theta times by tan theta over tan squared theta plus 1. Now I might just check those ratios up here. Tan squared theta plus 1. That's nice. That's sec squared theta. So let's use that. So I get 1 over sine theta times by sine theta over cos theta, which is my tan theta, over sec squared theta. What's sec squared theta? 1 over cos. So I get 1 over sine theta, so 1 over cos squared, times sine theta over cos theta, oops, times the reciprocal of 1 over cos squared theta, which is cos squared theta over 1. And of course, that cancels with that. That cancels with that to leave me just cos theta and a whole bunch of 1s. And so I'm left with cos theta. Now, having a look at my proof here, I'm pretty convinced there's probably a shorter way. And I'm also pretty convinced most of you wouldn't need to show every one of those lines are working. I'll leave that up to you, but that is one way you can do it. Yeah.
Would you just flip like everything around? So like cosec theta on the top, you could just make that sine theta on the bottom. Tan theta, you could just make that sine theta on the bottom, cos theta on the top. Because you just flip everything back.
I can do it with the cos, but I can't do it with those two because they're two individual terms on the bottom. Not until I make it one term. Then I could do it there, but it has to be one fractional term on the bottom.
Yeah.
So yes, the answer is yes, and I think that'll probably lead to a quicker solution, particularly with dealing with the cosec, but just be careful you don't do something wrong with two individual terms.
Yeah, okay.
Okay, that's me, and I am going to do the second part of this later this lesson, and I know that leaves things a bit short, but for now, you are hopefully able to do some of the questions from 14A, and I'm going to leave you to do that. And sort these videos out, and I'll come around and help you if you need. Oh, look at that.